Hello everyone. So this is the last section in this course on solid-state devices, and I'd like to talk a little bit about the modern MOSFETs, the challenges it has overcome in the last 10, 15 years, and some of the challenges it is still facing. So let's dive in. I'll start out with some of Moore's Law's challenges and give you an idea of why some of the scaling is important, and some of the effects that we anticipate are going to be big challenges down the line still. And then I'll give you a flavor for some of the work that has been done in the last 15 years or so to overcome various effects that have been a challenge, like the short channel effects, like the control of the threshold voltage, and mobility enhancements that have been pushed through. So let me dive in and show you again Moore's Law. Here's a different kind of plot. This one is actually kind of old already. It is taken from the Free Lunch is Over, and it's an updated set from 2009. So it's quite old. But what it shows here is the number of transistors on a chip as a function of years. And as we had seen in this incarnation of Moore's Law, it grows exponentially over the years. And even though this chart is old, we are today roughly at 10 billion transistors per die, per chip that is plugged into a CPU or your phone or a GPU are actually the ones that really have large multi-cores on them. So it does roughly keep going in this direction ballpark here. So we're roughly over 10 billion. So maybe it slowed down a little bit, but it still grew. Now, if you're as old as me, you might remember the days that people were all excited about their 486 PC now running a factor of 2 faster. And I never liked PCs, but okay. People were buying computers because they were running faster and faster. But if you bought and compared computers, know a little bit about the history of them, you will know that since about 2005, the clock speed has sort of tapered out at roughly 2 gigahertz. You can buy some that are clocked faster, and they spike up to 3 or so, or maybe some high performance units. But in general, your clock speed runs at about 2 gigahertz. So this is really true since about 2005. So clocks have not improved per se. The switching speed in the device, in the circuits that we have, has not improved. Now you can do things with architecture, multiple threadings, etc., by having more circuit elements, more transistors at the same switching speed. But overall, the clock speed has not improved much or increased much anymore. And that goes along ultimately actually with the power that is being consumed in these transistors. So that is sort of tapering out at 100 watts per CPU. And that is a core element as to why the clock cycle hasn't really increased in its speed. So I'll talk a little bit about more of that in detail. And then this chart here, this block, shows that really the performance gain from scaling devices as such is now limited. It isn't increasing up much. We gain performance overall by parallelism and multi-threading, etc. But overall, for the individual transistor, there's not a whole lot of performance gain anymore. Now, what's so special about this 100 watt? And that's in the context of VDD, the total voltage that is applied in the circuitry has stopped scaling, meaning becoming smaller since around 2003. So let's look at this 100 watt and see what makes it special. So here's a chart by Pat Gelsinger, who is an Intel employee from 2004. It's a little bit tongue-in-cheek. At that time, he basically stated, look, we have reached at 100 watt power consumption here, okay? 100 watt per square centimeter is the power density of a nuclear reactor. That's pretty hot. And you have to transport that heat away from the chip. And if you can't transport it away fast enough, then the chip will have damage to it. So there's an element of how do you cool such devices? And if you have mobile devices, how do you provide so much power through your batteries that you can keep this device alive? So there's aspects of power consumption that are limiting these devices. Now the fun part is, he said, if you just continue to increase as we have done and close your eyes and keep increasing or decreasing the voltage in your system, etc., you'll reach the heat at 1,000 watt per square centimeter of a rocket nozzle, or eventually the sun's surface. So obviously this doesn't work, but it puts it in perspective on how much energy in a small silicon chip is being consumed when it runs to full power in a CPU, for example. So 100 watt per square centimeter is one of the factual power limits in practical technology. So where is all this power being burned? So there's two big components. One are the devices and the circuits on the bottom. And the other piece is the interconnect that connects all these billion devices together. Since this is a device course, I'm going to focus on the leakage in the device and the power consumption in the device. So let's do that. What is the basic circuit element that really operates a chip? It's an inverter. It's basically holding the state of 1 and the state of 0 and pipelines that through some computation. And we haven't touched circuits much in this course at all. And you might recognize these two symbols. There's an NMOS and a CMOS device. And they're set in series to each other. And you can have a signal here on this shared line that might be high, that triggers this to be set to low, and vice versa. Okay? Now, how is power consumed in this? Whenever you change the state of the system, going from 1 to 0 or high to low, what you have is you might have a voltage here in the system that is ultimately charged up in some capacitor. It's holding some capacitor value, or it holds a voltage that is then being dropped over some resistive load. So that voltage then, or that power loss goes as the square of the applied voltage that you drop your charge over. And the amount of charge goes with the capacitance, and the frequency is how often you do that per second. So the dynamic power, the active inverting of this circuitry goes as frequency, capacitance, and supply voltage squared. Okay? So the beautiful thing about the CMOS technology when it came out early on was that power was roughly just consumed when it was switching, when it was really active. Okay? And that power, again, goes as frequency, capacitive load, and VDD squared. So what are your opportunities to save power? Well, you could reduce the frequency, run your computer slower. That wasn't really a good sales argument, was it? So you can work hard to make capacitances small, devices small, reduce the losses in your devices per se, okay? So that's a lot of work. And in the next subsections, I'll talk a little bit about a lot of that work in more detail, as short channel effects and threshold voltage control, etc., have demanded technology advancements. But it's a lot of work to do that. And it's still going on today to optimize technology, get smaller transistors. But it's a lot of work. But what has happened for some 30 years was a relatively easy step: reduce the voltage. Just to put this in perspective, you can reduce the voltage by a factor of 2, you reduce your power consumption by a factor of 4. So that's quite significant. to reduce the voltage in your system like that. And as I mentioned, the beautiful thing about CMOS technology was that it was only consuming power when it was switching. There is, however, another component in this power loss in the circuitry, which is the leakage. So regardless whether it is switching or not, one of the two transistors will be leaking some current, and I'll show that in the next slide. And that current will ultimately lead to some loss. Now, I'll show you in the next slide that the static power roughly goes as the inverse of the exponent of the supply voltage. Of course, you have to put in some Qs and KTs and some differential against some reference voltage. But the point is, as you make VDD small, your exponent gets really small. That means your off power consumption in the leakage is going up exponentially. And I explain to you why that is in the next slide. But the point is, there's a counteraction. I mean, it was nice to reduce the voltage, but we are now at a regime where it's important that you can't reduce it anymore. And I'll try to give you the reasons and the more physical intuition as to where that comes from. All right. Now, this is a chart that should be rather familiar to you. I used it a couple of times in the course. I open up the course with this in some of the opening slides, indicating this is how a transistor works, right? You might have electrons flow, and they flow even when the device is nominally off. And I introduced this chart as saying, well, it's going to create 1,000 questions. And my hope is that throughout this course, you have begun to get some answers to those questions. Now, you will now understand as I increase the gate voltage, I lower the barrier a little bit, and I expose more electrons that are sitting in the source and that are sitting in the Fermi tail of a density of states, and your transistor turns on. And it turns on at best at a slope of 60 millivolt per decade. Okay? And that number should be familiar to you as well, and where that number comes from should be roughly familiar to you as well. So, as you increase the voltage further, you eventually hit some threshold where the channel is really opening up, and then we calculated before saturation currents, etc., and you get your transistor curve that should look rather familiar to you now. Okay, so that's how the transistor works. And remember, I talked about Fermi function decaying exponentially linearly on a log scale, a density of states that goes as in a 3D system, it goes as a square root. We've calculated these things now. Now this should look rather familiar to you, okay? So, now we also talked about that this slope here is actually a very critical one, the 60 millivolt per decade. In reality, most transistors don't switch on quite as well, okay? And we'll talk a little bit more about that in the latter part of these sections. Ideally, what you would like to have is a transistor that just turns on with very little voltage action, right? And is almost square, okay? That would be an ideal transistor. But what a CMOS device can give you is at best this transistor, okay? At best this overall shape with a slope of 60 millivolt per decade at room temperature. And this is the origin of the 60 millivolt. You know about the various capacitance in the system, etc. Okay? So, now, what's the problem with reducing the supply voltage? So here's your perfect transistor operating at 60 millivolt. Again, most likely it's not quite as steep. What happens if you reduce this voltage, the VDD supply, right? It's kind of like taking the best transistor you have and shifting the voltage over, and we talked about how to do that with a threshold shift, etc. And you can shift it a little bit more, and notice that this current here, log of drain current, is on this log scale. It goes up linearly on a log scale. That means it's growing exponentially. So your leakage is growing exponentially if you're pushing your transistor such that you only have a few decades in terms of amplitude here left over, and you're pushing up exponentially your leakage current. All right, so that is what has happened over the years, and you get to this leakage through the transistors. And there's actually data that has been published by Eric Popp quite some years ago, where he is plotting the dynamic power in these transistors over, these are now technology nodes or gate lengths, okay? So think of this as a historical axis going backwards. We got devices that are smaller and smaller, the gate length got smaller and smaller, and the dynamic power has risen moderately. But the leakage power, as indicated here, has risen exponentially. And in today's technology, these two are roughly of the same ballpark size. In fact, you can argue the leakage power is larger than the switching power. So that means this ideal, cool transistor from 30 years ago that only consumes power when you turn it on and off is now consuming power all the time. As soon as you apply a supply voltage, it is consuming power, whether you're switching it or not. So you have to do special circuitry to shut off segments of circuits that you don't need, depending on the compute load, etc. So people have gotten really sophisticated in managing this kind of power. But the origin of this, you now understand. Why is this device consuming so much power now? Okay. So the question is, how do we get away from this exponential dependence, right? We would like to have switches that consume less power. So the ideal thing would be to have a switch that is not limited to this slope here, and in reality actually looks more like this. Think of this as being a spaghetti that you can push over, and you'd like to have, in the ideal world, a switch that looks like this, right? So you can reduce the slope. You want to reduce this sub-threshold slope to less than 60 millivolt per decade. So there's a whole field of device engineers and researchers like me that have been hunting for a switch that has this characteristic. And you have to now understand what are the fundamentals of this 60 millivolt per decade, and can you overcome that with some trick? Or if you apply this trick multiple times, then it becomes a method, right? So what might be one of the candidates? Well, the fundamentals of the normal CMOS you now understand. Now I'm going to sketch for you one potential alternative that might reduce your leakage current. So let's imagine you have a sea of electrons as indicated here. In this case, we have indicated here the Fermi level, and you know that the Fermi tail is really creating the 60 millivolt per decade, right? Now, the Fermi function is always going to be there. You can't really change that unless you reduce the temperature in the system. So the other factor is the density of states, which is the number of electrons in the system is the density of states multiplied by the occupation of such states. So what if you could prevent electrons to be here? What if you could put a band gap here? Okay? And what if you put a band gap into the channel like this, where if in the off state, electrons cannot make it through all the way? And what if you then have another way where you can have a gate that pushes this band gap down? So what this is here really a PIN junction in the simplest of all sketches, where you have, here's the junction translated down, here's the next junction translated down, and you have a gate that pushes this potential up and down. So your barrier material is somewhat independent of temperature, but it's truly shutting off the density of states. People talk about a term like cold injection. It doesn't matter what the temperature of the electrons here is, it's looking at the density of states. You can also look at this as a bandpass filter that we discussed early on in the creation of band structure, okay? Now, with that, you could imagine that you can reduce the voltage quite significantly. And that would be one candidate to pursue. There's another candidate out there that looks quite promising as well. That's the NC FET, the negative capacitance FET. So I'll invite you to study that as well and get some overview. This tunneling FET, the tunneling device, is actually very hard to build. Electrostatics are complicated. You really have to understand how these bands move, and then there's band tails. There's all kinds of complicated things going on. And it may not happen. That's how it looks right now. In 2020, there is no TFET in sight that is going to make it into production. But at least conceptually, it looks pretty easy. So, speaking of putting things into production, I'd like to show this roadmap that is actually a couple of years old now. It's over 10 years old, I believe. And it gives us a perspective how industry has planned the development of technology nodes, of transistors, about 10 years ahead. So they have a pipeline of technology out there. So in 2011, they had planned to come out with a 22 nanometer transistor, and we've shown that before in the class. It's the first three-dimensional transistor. And then they have their further plans out. And at that time, there's all kinds of interesting things like graphene on the chart here, some molecular things, some photonic devices. So there, whatever is like 8, 9 years out, 10 years out, they look at it as a very exploratory thing. Now today, you can actually buy transistors that are sort of on this scale here, right? You can buy 10 nanometer technology. All right, so let's focus on this 22 nanometer node, which is the Intel 22 nanometer FinFET. Okay, so here is sort of a solid model, like what a mechanical engineer might use, or what actually any device engineer, if you lose any commercial product that's out there to do device modeling, you would get a solid model like this. And what you see here is this fin, and the cross-section of this fin is marked in blue. And you have this gate that is wrapped around here. So the electrostatics are very good, and you can control the electron flow in the device quite well. So short channel effects are taken care of very well, and we'll discuss that in the next subsection. But what I'd like to highlight here as a challenge for the future is, let's look at this blue cross-section here in a little bit more detail. So here's an SEM of this of such a cross-section, and this fin is 8 nanometers thin. So 8 nanometers. 8 nanometers. Let me translate that to you. That's 64 atoms. That's very, very few atoms. And nominally, if you translate 22 nanometers in length in silicon, you get 176 atoms. The actual gate is larger, but I'd like to make the point, those atoms counts are actually very finite. We're no longer talking about Avogadro number of atoms or Avogadro number of electrons in the system anymore, okay? So what you can do is also make a plot of such a cross-section or a fin in an atomistic modeling tool, and you find that there's about 1,000 atoms in this cross-section. That's, again, this is not 10 to the 23 anymore, even if you make this then repeat in 3 dimensions like this, right? That number of atoms is still very countable. And that's the challenge, really, that we pursue in the research group that I have, where we build tools that help understand this kind of transport in devices that are atomically small. So let me translate these nanometer nodes. That's in a way a description of the technology development. So you go from 22 nanometers to 14 to 10, 7, 5. If we just go roughly calculating how many atoms does that correspond in as a chain of atoms in one dimension, you're going down to tens of atoms being the nominal gate length. That's incredibly short. Now, if I look at what I call the critical atoms, in the case here for the 20 nanometer nodes, I had shown you 64 atoms in the cross-section. That goes down to tens if geometry doesn't change, etc., right? So this is just sort of a rough idea. The point is, it's incredibly small, incredibly countable, and it's not a continuum representation of matter anymore. It's really discrete. And that is what the software we built in my group. It's called nanoelectronic modeling, where we build tools that model electron flow in such systems, and this software is now being used in industry to understand those kind of devices as well. What few people talk about, this is still very interesting to think about, is that if you look at the number of electrons that are sitting on this gate capacitor, it's going down to tens. Normally you might think again of electrons as being this continuous wave of a gazillion plus one electrons, but we're going down from a few hundred now to some tens. And there's a whole world of people that study single electronics out there, and some of this is really relevant to quantum computing. There's big challenges on single electronics, but there's still challenges out there that might be an alternative to think about how to make switching circuits and logic circuits in a different way. So, that being said, we're going to look at some real things that have been solved to get us to where we are on these devices today. So the next one will be short channel effects. So I'll see you in that section. Thank you.